Welcome to Code Disclosed. In this video, I will go over the Gauss-Seidel iterative method and how to use it for solving a system of linear equation of the format ax equals to b. First, let's go through the main ideas of this method. So the Gauss-Seidel method is an iterative method that is used to determine the solution of a system of linear equations, just like this one, which its coefficient matrix is diagonally dominant. Now, the Gauss-Seidel method is an improvement over the Jacobi method. I went over the Jacobi method in another video. I will insert the link of this video if you'd like to go through this video and see how the Jacobi method is implemented for solving a system of linear equations. But the Gauss-Seidel method is an improvement over the Jacobi method. The main idea of the Gauss-Seidel is that, so for example, for the Jacobi method, the value of the variables is not modified until the next iteration. However, for the Gauss-Seidel, the value of the variables are used once they are modified. So we don't wait until the next iteration so we can use the modified variables. We use the values of these variables once they are evaluated or once they are calculated. Of course, this would reduce the number of iterations, as we will see in a moment when we go to the MATLAB code. It will reduce the number of iterations, and also it will converge to the solutions of the unknowns much faster. So I went through this idea in the Jacobi method video, but I'll go through it again because it's also very essential for this condition to be satisfied for the Jacobi and the Gauss-Seidel methods to be implemented or to be successful. The coefficient matrix for this system of linear equations must be diagonally dominant. What do I mean by this? So for example, if I have this, I have n equations with n unknowns. I can write these equations of the form in the shape or in the structure of ax equals to b. So what's this? A is the coefficients matrix, the coefficients of the unknowns. X is the vector of the unknowns, and b is the vector of the right-hand side. So if I want to apply this structure to this system of equations, so for example, the A here is the coefficients matrix, so it's A11, A12 for each equation. The x, however, is the unknowns vector, and the b here is the right-hand side. Now, when I say strictly dominant, I always look at A matrix. It's the coefficient matrix. Now, how to make sure that this matrix is diagonally dominant? So the main thing is to look at the diagonal entry. The diagonal entries at each row. So for example, for the first row is A11, for the second row is A22, for the final row is ANN. These are the diagonal entries. Now, for this matrix to be diagonally dominant, the absolute value of each of these diagonal entries must be larger or equal than the sum of all the rest of the entries of that arrow. So for example, for the first arrow here, the absolute value of A11, which is the diagonal entry here, must be larger or equal than the absolute values of the sum of all of the other elements of that arrow. We need to apply this for each arrow, and this condition should be satisfied for each arrow. If any of these arrows, if this condition is not satisfied on only of any of these arrows, then this matrix is not diagonally dominant, and hence the Gauss-Seidel method can't be applied, or in other words, can't converge to the right solution of the system of linear equations. All right. Now, to make things clearer, let's apply this on an example. For example, I have this system of linear of three equations here with three unknowns, x, y, and z. So first, let's apply this, or let's write this in the format of ax equals to b. So for A, which is the coefficient matrix, for the first equation, I have 4 minus 1 and plus 1 for x, y, and z. And for the second equation, I have 4 minus 8 and 1. And for the last one, I have minus 2, 1, and 5. These are the coefficients of the unknowns. X is the unknowns vector, x, y, and z, and b is the right-hand side. All right, let's look at the diagonal entries for A now. So for the first row here, is the absolute value of 4 larger or equal than the absolute values of the rest of the entries of that arrow? Well, yes, that's satisfied. For the second row, the absolute value of 8 is larger than the sum of 4 and 1. And the absolute value of 5 is larger than the absolute value of 2 plus 1. So this is satisfied, and we can say that this matrix is diagonally dominant. I'm going to do a very simple trick here for this system of linear equation. I'm just going to swap between the first equation and the last equation. That's the only thing I need to do. I'm going to write them again in the structure of ax equals to b, and I am going to test A now, if it's diagonally dominant, if it stays diagonally dominant even after swapping these two equations. Now for the first arrow, I have the absolute value of 2. Is it larger than the sum of the absolute value of 1 and 5? Well, it's clearly not. For the second row, is the absolute value of 8 larger than the sum of 4 and 1? Well, yes. For the third row, is the absolute value of 1 larger than the sum of 4 and 1? Well, clearly not. Since this condition is not satisfied for the first row and the last row, then I can say here that this matrix is not diagonally dominant. And you can see here that for the same system of these equations, just by swapping the first and the last equation, the matrix could turn out to be not diagonally dominant, and hence we can't apply Gauss-Seidel iterative method here, or in other words, it won't converge to the right solutions of x, y, and z. Now, the question here is how to code this using MATLAB. So let's move on to MATLAB now and see how to apply Gauss-Seidel equation and Gauss-Seidel method in this case. So these are the three equations that I used in the PowerPoint I showed before. So what I'm going to do here, first I'm going to define guess values for these unknowns. So for example, I'm gonna say x1 equals just 13, for example. These are just arbitrary values. You can put any values you would like, and I want to test if this method would converge to the actual solutions. So 13 minus 5 and pi are just guess values. All right, let's go through iterations. So I'm going to go for j from 1 until 10, for example. So I have 10 iterations. We'll check if we need more iterations, but for now, let's stick to 10. So x1 j plus 1, which is the next, it's the new value of x. I'm gonna say it's 7 plus y1j. So I'm solving for x for the first equation here. Minus z1j, and all of these are divided by 4. Now, I want to calculate j plus 1 now, so I want to evaluate y from the second equation here. So if I want to evaluate y, I have 21 plus 4 times x1. Now I already calculated x1j plus 1. Why don't I use it? So I can write here x1j plus 1, which is the value that I already calculated from the first equation. So this is the main idea of Gauss-Seidel method, is that we can use the new value of the unknown rather than waiting until the whole iteration is completed. All right, so plus Z1, well, Z1 hasn't been calculated yet, so it's still J, and all of this divided by 8. All right, let's go to J1 now, and sorry, Z1, and let's calculate the new value of this unknown. So it's 15 plus, so this, I'm evaluating Z from the third equation here. So it's 15 plus 2 times x1, so x1 is already calculated, so it's j plus 1. That's the new value, and now I have y1. Also y1, it's all already calculated from here, so why not using it? So here I can say over 5, and let's close the loop. So in this case, in this loop, it will be go over 10 iterations, and in each iteration, we are using the values of these unknowns that are already calculated within the iteration, rather than waiting until the iteration is done. All right, now let's plot it. Let's plot well, before. Okay, let's plot the values, or the final solutions. So I need now to plot x1. I'm gonna go with blue, and I want to plot y1. I'm gonna make it with red, and then I want Z1, which is, I want it in green. Now, this 111 here, I just want a vector on the x-axis where I can see these x1, y1, and z1. So they are just values, or a vector that will help me to plot. Let's run this, and hopefully there will be no errors in this. Okay, now you can see here that eventually, after the third iteration, third iteration, you will end up with x equals to 1, and y, I think y equals here to 4, and z here equals to 3 somehow. Is it 3? Yeah, I think it's 3. So after the 3 iterations, the Gauss-Seidel iteration was able to converge to the right solutions for these 3 equations, just from very arbitrary equations. What I want to do now is I want to and by the way, these equations, or the coefficient matrix for these equations, are strictly dominant, diagonally dominant. That's why it converges here. I just want to do a comparison here. Comparison between Jacobi and Gauss-Seidel equation algorithms. So I just want to see how fast or how efficient Gauss-Seidel is compared to Jacobi. I want to say, okay, x2, for example, let's do, you know what, let's do x2. All right, let's copy these, and let's do a new ones here, 2 and 2. And let's go through the iterations, but now using Jacobi method rather than Gauss-Seidel. So I'm gonna copy this, but as we said before, in the Jacobi we don't use the newly evaluated values. We just use the same values, and the new one will be used after the whole iteration is done. Okay, so this is Jacobi now, and let's do a new figure, and let's plot exactly the same thing, but now I want to plot x2, y2, and z2. I just want to see how fast is Jacobi compared to Gauss-Seidel. Okay, let's run that again. And let's see. All right. I didn't change these here. So all of these are x2, y2, and z2 for the Jacobi method. All right, here we go. So this is the Jacobi and this is Gauss-Seidel. So figure 2 is the Jacobi and figure 1 is the Gauss-Seidel. And you can see that for the Jacobi, until its iteration 5, the method or the algorithm was able to converge to the right solutions of x, y, and z. However, for the Gauss-Seidel, it took 3 iterations only for this algorithm to be able to converge to the right solutions. So you can see here that just by using the newly evaluated value for the unknowns within the same iteration, rather than waiting for the whole iteration to finish, it clearly saves time and saves computational time, and make this algorithm reach to the right solution faster. So that's all about the Gauss-Seidel method. Hope this was helpful. I will put the link for the GitHub link down in the description box below, that contains the code for this video. Hope this was helpful, and I'll see you in the next video. Thank you very much.